Hello and welcome back to BME 2315. In this in this video, we're going to be talking about interpolation. So as a motivating data type, we're going to be looking at, in problem set 6, at cardiac MRI data. So MRI, or magnetic resonance imaging, creates just absolutely beautiful videos of heart contraction, and I encourage you to watch some of these at the link below. Here, let's just take a quick look. So absolutely stunning images, as you can see. And what we're going to be doing is looking at this particular data set in which is measuring the volume of the heart as it contracts. And so it starts large and then it contracts down to a smaller volume at what's called systole, and then rests, and as the heart relaxes, it goes back to a larger volume. And ideally, we'd like to calculate the half contraction time, or the time that it takes to go halfway to its full contraction. However, we only have a few data points on this, and so calculating the half contraction time based on these data values would not be very accurate. And so to solve this problem, we're going to use interpolation. And interpolation allows us to estimate intermediate data points in between the precisely known data points. And so we can get a more accurate measure of the exact timing at which we get halfway to contraction. These are some of the learning goals for this section. I encourage you to look them over once we've completed the topic. Before we get into interpolation, let's take a look at just a very quick review of the topics we've seen so far. Taylor series starts with a function, and that allows us to estimate next values of a function. Differentiation takes sample data points and calculates the local derivative or slope of the curve or data. Integration, instead, takes sample data points and calculates the integral, or the area under the curve. And finally, what we'll be talking about today is interpolation, which also takes sample data points as the input. And what it does is it calculates intermediate values or internal data points between the data points that you already know about. So interpolation is about estimating intermediate values between data points. And so there are two types of interpolation. One is in polynomial interpolation. And in polynomial interpolation, we're finding the polynomial that exactly connects n data points. So if we have n equals 2 data points, we can see that we can interpolate or estimate the line that exactly connects those. So that would require 2 data points. Or a quadratic right here if we had 3 data points. The 3 data points, and so it's n minus 1, so 3 minus 1 is 2. So a quadratic is what connects 3 data points. Or finally, we'll be talking about B-spline interpolation at the end. And that, instead of calculating from a single polynomial, calculates a piecewise function that approximates or gives us the internal data points in between these values. And so B-spline interpolation works for n data points. Okay, so the first type of interpolation is linear interpolation. So let's take a look at how that works. So basically, we're going to start out with 2 points right here, and we're going to be trying to find the line that goes through them. And so the interpolating function is just a line, as you're very familiar with. And how do we find that line? Well, like in a traditional approach back in basic algebra, we would calculate the slope and then the y-intercept okay? So that works, but it's not very scalable. And so what we're going to do now is look at a matrix approach to this that will help us see how to get this to work in general. So in matrix form, you could write y1. So we've got a general equation of y-intercept plus the slope times x, and we plug in the specific values that we've got. And y2 was a1 plus a2 x2. And so now we can rewrite this as matrices. So we've got a y vector that's 2 by 1. Was 1, x1, x2. This is a matrix that we call Z, which is going to be 2 by 2. And then we have a matrix called A that is going to contain our coefficients. Okay? And then we can, so we know all the x's, we know the y's, we're solving for the unknown A. And so to solve for that unknown A, we could either use a Gaussian elimination or in Python, np.lin alg.solve, and we'd be solving z and y, z, y. Actually, this would be a capital Y. Okay, so there's like basically a one-step solution once you set up the matrices as you see here. So that's how linear interpolation would work. So let's take a look at an example applying that. So say we've got this natural logarithm equation, as you see right here, and we're going to take a look at assuming that we know data at 3 of the points, at 1, 3, and 5, and we're going to be trying to interpolate or find the line. I'm sorry, we're not going to be using the one at 5. We're going to be using these 2 data points to interpolate to estimate what y2 is. So we're going to be looking for the line that goes right here. Okay, so the way that we're going to do that is we're going to set up our matrices as we saw in the last slide. So we got 0 and 1.099. These are the y values corresponding to the 2 points that we've got. And then this equals, we've got a z matrix that's always 1s in the first column, and then 1 and 3, because those are the x values that we had for those two points. And then finally A1 and A2 in our A matrix. And those are the unknowns that we're solving for. So we're going to solve this linear system. I'm going to say A equals, I'm just going to write solve, but remember in Python it's the NP is np.linalg.solve. Okay. So if you solve given z and y, and then you run that, you'll get negative 0.5495, 0.5495. Okay. So that just solves the coefficients, and so now we need to be able to plug this back into our equation to estimate what the actual value is at x equals 2. So f1 x equals is where I'm plugging in my coefficients. So this is the linear interpolating function. It's the line that connects from x equals 1 to x equals 3. And then f of f1 is 0.5495. Finally, if you then compute the true error, remember you're going to compare this 0.5495 to the 0.693, where that's the true value. You would find that the true error is about 20%. Okay, so it didn't do that great of a job. So that's how you would do a linear interpolation. What if you have more data points and you'd like to get a quadratic interpolating function? So this is what graphically this would look like. You've got 3 data points, y1, y2, and y3, and we're going to find the quadratic that that interpolates, that goes exactly through these 3 data points. And one really important concept is that for n data points, there's only one interpolating polynomial that will go exactly through those data points. So there's only one function that's a quadratic that can go through these 3 data points. Okay, so we're going to set up this problem much like the last one in a matrix form. We've got y1, y2, and y3. In a y matrix, that's 3 by 1. We've got a z matrix. That's x1, x2, x3. So far this looks like the linear interpolation, but now because it is a quadratic, we have an additional column here. Okay, and that's z, which is 3 by 3. And then finally we've got our coefficient matrix. Because this is a quadratic, there are 3 unknowns. Okay, so you would set up this system like this, and then you would solve for A with A equals solve C Y. Okay, so let's take a look at an example of that one. So just so you can see how you would actually apply this quadratic interpolation. So similar to before, we're going to be interpolating this natural logarithm, and we're going to be using points at 1, 3, and 5 to find the quadratic that goes exactly through those data points. Ooh, sorry, there's a delay on my pen, and it got way too far. Okay. All right, well, I'm going to give up on drawing an accurate quadratic right there. Okay, so we're going to start out by, in matrix form, we're going to specify the y's that we're using to solve this y. Then there's a z matrix that's always 1's in the first column, then x's on the second column, and squares on the third column. That's z, and then a1, a2, a3. Okay, and we're going to so A is the unknowns, so we're going to solve this linear system. Solve given z and y. And what you get back from Python should be this. So this little vector. And then, so this is the coefficients. And so then, in order to find out what the interpolated value is based on those coefficients, we need to plug them in. So f2 x equals for x minus this times x squared. And if you plug in the x value, f2 at x equals 2, you should get 0.6231. And if you compare that to the true value at natural log of 2 is 0.693, and so you should find that the error is about 10%. Okay, so we've gone through linear interpolation, quadratic interpolation, and so finally what I want to do is leave you with how this looks like in general for higher order polynomial interpolation, and have a single equation that covers, or a single framework that covers any order of interpolation. So basically, if you have say a more curvy looking function like here, and we have like x1, y1, y2, x2, x3, y30. So it could be a lot of different points. And the point here is that it's going up to something higher, some nth data point, y to the n. Okay. Then what you can do is the interpolation has the same exact pattern as we saw before, that we just set up these matrices so that y1, y2, dot, 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 to yn is y, and so this is of size n by 1. Our first column is all 1s. Our second column is all x's. And our last column, x1 n minus 1, x2 n minus 1, x the n minus 1. So z is n by n. And then we have our unknowns matrix. A to the n. And that's A. To solve this, we're just going to use z and y. And then to interpolate new values, because that would have given us the A values. So to interpolate new values, it's just y equals za. Once you've solved for the a's, you can just multiply that by a new z matrix, in where you're putting in the new x values where you want the signal to be interpolated. Okay, so that's how you do polynomial interpolation, and in the next video we'll talk about B-spline interpolation.